Hello all and welcome back to this course on computer organization. So we have been looking at taking a C program to assembly language in the past week, and I think it's the right time for us to also look at how data is stored in the memory. Okay, there are certain nitty-gritties that we need to be aware of in order to appreciate why the compiler actually does some things in a certain way. Okay, and one of the most important things to remember, right, is the concept of memory alignment. Okay, so what is memory alignment? Memory alignment basically tells you that there are different kinds of data that you might want to work with, right? One is bytes, other is words, 16-bit or D words, 32 bits. You also have larger chunks of memory called pages, which is 1 kilobyte bits, and so on, right? Now, when you want to store such information in memory, it cannot be stored at arbitrary locations. Okay, there are certain rules that need to be followed. Okay, for example, if I look at the address on the first column here, right, going from 000 all the way to 007, right, the data is some, of course, each memory location is 1 byte because it's byte addressable, and let's say I want to store 2 bytes and 1 D word of information, right? In that case, such a storage is simply prohibited. Okay, so what I am doing here is I am storing 1 byte 0x01 in address 0. The next address I am storing another byte, which is perfectly fine. There is no issue there. Okay, so remember that a byte can be stored in any memory location. Okay, so there is no constraint on storing a byte of information. However, when you're storing a D word, it has to start in multiples of 4. So in this case, we are starting it at location 002, and therefore that is a problem, right? The computer will not allow you to do that. Why? Simply because the way memory is organized, there it will incur a significant latency hit if D words are stored across you know uh, uh, multiples of 2 and all that stuff. And in fact, when you go to pages of memory, right, that becomes worse because it will span multiple DRAMs and all that stuff. So effectively you can have a significant performance hit if you don't follow this memory alignment principle. Okay, and that's why compilers will be very careful about this. So instead of doing it this way, which is prohibited, where the D word cannot be stored like that, what you have to do is to give a certain gap in the memory, and then you store the D word in this particular way. So what is happening now is the D word is being stored in starting at 004, right? And the 2 bytes of memory here are completely wasted. Okay. However, if you want to store a word of data, right, which is just let's say 0x 0e 0x 0f, if this is a word of data, right, then this is permitted because the word can start in multiples of 2. Bytes can have to go in multiples of 1, and D words have to go in multiples of 4. Okay, so this is the concept of memory alignment that we need to be aware of, right? And when you take this to a compiler, some funny things can happen, and you need to be aware of it and understand it to appreciate why it is being done that way. Okay, so another important point is also the endianness of data. Endianness. Okay, Endian. There are two types of two ways in which data can be stored. One is called the little endian. Okay, and the other is called the big endian. Okay, so there are two ways. So what is this concept? It's very simple. You take a memory location, right, and this is increasing. The arrow indicates increasing memory. Increasing memory. So this is some location A plus 1, A plus 2, A plus 3 and so on, right. So I have, let's say I have 4 bytes of memory location like this, and let's say I want to store 4 bytes of data like this. So 0A, 0B, 0C, 0D, and I'll also put the same thing on this side. Okay, so this is my LSB, least significant byte, okay, and this is the most significant byte. So likewise out here I'm doing the same thing, 0B, 0C, 0D, and this is the MSB and this is the LSB. Okay. So now what you can do is you can store this data in 2 different ways. The least significant byte can go into the lowest memory address, okay, because I have now a D word contains 4 bytes, okay. So how you store in which order is a convention, and that is what we are discussing here. So the least significant byte can go to the smallest address and everything else follows accordingly. So the most significant byte will go to the largest address. Likewise, the most significant byte can go here, okay. That's why you note that I have not mirrored this data. The 0A, 0B, 0C, 0D order is the same on both sides, okay. Okay, this is called Little Endian, and this is Big Endian. Okay, just it's sort of useful to know these terms and conventions. I don't think there is any big advantage of doing it one way over the other. Okay, it's just a convention. Most processors follow the Little Endian format. Some of them do follow the Big Endian format. Anyway, so this is the low level constraint that the computer or the memory imposes on the computer. Okay. How does this translate to the compiler, right? What constraints do the compiler see? What does the compiler have to worry about when actually handling such constraints? So let us look at a very simple C program which I have written here, as you can see. Okay, what we have basically done is we have a main in which I have an int x1, character ch1 and ch2, these are all local variables, int x2. So where are these variables going to reside? They are going to reside on the stack. Okay. Then I have this char star p test, okay, some string pointer, okay, which is basically going to point to this is a test string. Okay, so it's going to the string called this is a test string is going to test character string is going to sit somewhere in the memory, and the char star p test is a pointer. Okay, it's a pointer that is going to point to this string. Okay, so now what I am doing here is I am simply doing printf ch1 and I am saying %x. What is %x? I am just doing a hexadecimal printing, okay, and I am printing the address of all these things here, okay. So if you look at this, let me take this out for now, right. So what I have basically done is I have done printf ch1 ampersand %x, and as arguments to printf I have passed ampersand ch1, ampersand ch2 and ptest, ampersand x1 and ampersand x2. Okay, so The important thing here is I am allowing the the compiler is going to assign some addresses to this x1, ch1, ch2, x2 and all that, and we are going to see now how all this is going to follow the memory alignment constraints that I just spoke about. Okay. After that, what I am doing is I have another function fn, okay, which takes an integer x1, a character c1, integer x2 and character c2. So deliberately what I have done, I have made it alternate integer character, and then I am doing exactly the same printf, okay, inside that function fn. So if I run this program, right, what you will basically see is you will see the addresses of these variables, local variables being printed first, and then you will see the address of these function parameters being printed next. Okay. So let us look at, let's just get this thing running here and then we'll see how to this thing. Okay. Okay. So what we are going to do now is we have a very simple C program here, okay, where we have a main. In that I have local variables x1, which is an integer, character variables ch1 and ch2, and another integer x2, okay. And some, don't worry about the functionality, I am just doing x2 equal to x2 plus x1 here, it does not matter one bit, okay. So what I am going to do now is I am going to change this program a little bit from here, right. So I'll do this. Okay, so in order to understand memory alignment from the compiler's perspective, let's look at this simple example. I have a main, I have integer x1, which is the local variable, characters ch1 and ch2, another integer x2. Where are these local variables stored? They are all going to be stored on the stack. We already saw this and they will be addressed as EBP minus some offset, okay. Then I have this char star p test, which is pointing to a constant character string, which means that this is a test character string is going to be sitting in memory somewhere and that address is going to be assigned to this char star p test, okay. So what I am doing after that is I am doing printf ch1 equal to %x, okay. What is %x? It is doing hexadecimal printing and the arguments I am passing, right. So I am saying ch1 equal to %x, ch2 equal to %x. I am basically printing the addresses of all these local variables, ch1, ch2, ptest, x1 and x2, okay. So they are all basically going to be addresses of integers, characters and strings essentially. Then I am calling this function fn, and what is the function fn? It's, I have just a definition here sitting on top, so I don't need a declaration. So fn of int x1 character c1, int x2 character c2, then I am doing printf, an identical printf that I did in main. I am printing the addresses now of these function parameters. So remember that when a local variable is actually passed as a function parameter, what happens? That a copy of that local variable is pushed onto the stack before calling that function, right? You push right parameters right to left, set up the stack, call that function, and then you enter the context of that new function, right? So therefore these function parameters have different addresses on the stack compared to the local variables themselves. We are not passing the address directly out there, okay. We are not dealing directly with the local variable of main in that function fn, right. So what we are going to do now is we are going to look at what addresses are getting assigned here, not the exact absolute values. We are interested in the relative positions of these variables, okay. So let us first understand what happens in main. Okay, so the first printf that you see here, right, is what you are going to see in main. So what I'll do here, I will add a tag like this, main, so that we know it is coming, the printf is coming from main, right, and the other one is obviously going to come from the function fn. Okay, so when you execute this function, it turns out that the printf coming from main is actually putting out such addresses for you. Okay, let's just look at these addresses a little carefully.